Hello everyone, welcome back to 3120. Today is going to be the last lecture on this section here where we've been talking about catalysis and condensation and how we can control these different reactions using specific enol equivalents. So what we're going to focus on today is the use of specific enol equivalents with acylation of carbon, and we'll look at some specific examples also in terms of acylation of enols under acidic conditions. So here's our little roadmap. We finished that. So lecture 23. So we'll call this specific enol equivalents with acylation at carbon and acylation of enols under acidic conditions. So I guess a little bit of a mouthful there. Okay, so one of the issues that we talked about with enolates, and if we're acylating them, so let's say we have some acidic proton and we form an enolate. One of the challenges that we identified a couple lectures back was that you could inadvertently get attacked here to give you an enol ether, which is not your desired product. So if we're using some kind of base, and maybe a strong base, we can typically think of counter ions to stabilize that enolate. Often we can think of things like lithium or sodium or potassium. Now recall, lithium had very good ionic bond character with oxygen, has pretty similar atomic bond radii, so you get pretty good overlap. As soon as you start going to sodium and potassium, then you start weakening that bond and thus making this a little more reactive. So how can we ensure that the carbon will be the better nucleophile? So what we want to get is this coming here and this attacking, as I'm showing here. You do not want that above approach. So typically it's best to use lithium enolates. So try not to use sodium enolates or potassium enolates. Again, it's not perfect. The lithium enolate is still pretty reactive, but at least if you do use a lithium enolate, you have a very strong ionic bond, as I'm showing you there. Okay, very, very good. Like I said, it's not super reliable, so a more reliable approach in using specific enol equivalents involves using a weaker nucleophile. This would be an enamine, which we learned about already. So let's go through that. So if we start with cyclohexanone and we want to make an enamine, you remember the conditions and the recipe for that. Secondary amine, catalytic protons, and that will generate your enamine as I'm showing you here. And then if you take something like an acyl chloride or an anhydride, you have a much better chance of this reacting at this carbon, like I'm showing you here. Form your tetrahedral intermediate. You have R2 here. That's positively charged. You collapse your tetrahedral intermediate. And as you've also learned, these at the end of this, you get your imine, your positively charged amine. You have to hydrolyze using just water and some acid. So again, we won't go through that mechanism, but you know how to do that. And here's your product. Now you might say, okay, that looks good on the chalkboard or on paper, but why don't we have to worry about the nitrogen attacking? So let's take a look at what might happen if that nitrogen attacks. So if this nitrogen attacks instead of the carbon, let's go through what this would look like. So this is undesired. You don't want N-acylation. Your nitrogen is now positively charged. Okay, and it's going to look something like this, tetrahedral intermediate. Then your oxygen will come down, form the pi bond, displace off the chloride, and what you're going to have is chloride anion like this, and you generate this compound here. Now, I want you to think about, is this going to be a stable product? In fact, what you've generated is an acylating agent. You have attached to this carbonyl group a really, really good leaving group. You have this positively charged nitrogen. In fact, think back to our introductory lecture a few weeks back, in which we looked at the base catalyzed protection of alcohols, I believe. And this involved forming, or the base reacting with something like acetic anhydride to make an even more reactive group. So you can think of this as being now a really good leaving group. So if you think of this being formed and you have chloride present, well, what's going to happen is that all these steps are now reversible, right? So the chloride will come back, electrons will go up, right? They'll come back down, and then you'll displace back off that enamine, okay? So while the nitrogen can react, it doesn't lead to anything productive. So that's why nitrogen is okay in this state if it reacts with the acylating partner, because it'll just go right back. Every step is reversible. All right, so enamines are good choices. The other one that we spent quite a bit of time on involves Aza Enolate, so let's take a look at that. Aza enolates also react exclusively at the carbon. So let's just go through an example. If we take this compound here, and let's say we treat it with a primary amine, so that's a primary amine with catalytic protons. You're going to generate first an imine, okay, so it's dimethyl nitrogen, nitrogen bond, NH2. So you generate your imine, and then when you treat this with a strong sterically hindered base, so something like LDA, you're going to take the least sterically hindered proton and form that Aza Enolate. And the Aza Enolate, it is negative. You can think of this like a negative nitrogen, but very good electron donating, right? Especially compared to oxygen, right? Which is more electronegative. So the nitrogen electrons will come down and then you'll react with your acylating partner. So it's a much more reliable approach compared to something like a lithium enolate or even just an oxygen, any kind of enolate. Okay, so just to complete this, what you'll end up generating is this tetrahedral intermediate. Electrons go down, chlorine gets displaced off, and then you have your amine that you still need to get rid of, right? Because you're forming, you got to go back to your starting ketone. So again, just like we had done over there, remember your third step is always going to be removal or hydrolysis of this, and that's with water and acid. Yeah, very good. So it's like a 1, 2, and then your acylating partner is like step 3, and then step 4, add water and hydrolyze it. All right, good stuff, right? So all those specific enol equivalents are being put to good use. So let's look at a couple specific examples of acylation of enols under acidic conditions. So there are some instances where we can do some interesting chemistry using very mild and gentle conditions. And while these solutions here that I'm showing you are actually quite good and quite valid, it is a lot of work to make a lithium. To use LDA, as I mentioned before, you have to keep this cold at like -78. It's very reactive. Even acyl chlorides are very reactive. So are there some gentler approaches that we could use under specific circumstances? So let's look first at the acylation of enols under acidic conditions. As an example, here is going to be our substrate, our starting material. And we're going to use something called polyphosphoric acid. Okay, so polyphosphoric acid, something that looks like this. It's like, phosphoric acid, but you have a polymer, and I'll just sort of highlight that you could have, a monophosphate, diphosphate, triphosphate, and it's usually a mixture. And then what you have are these weakly acidic protons. Okay, so it's a weak acid. And what so this is called PPA, or polyphosphoric acid. What polyphosphoric acid is good at doing is taking carboxylic acids and further protonating them. And I'm going to show you what happens. So so let's do this right now. So I'm just going to abbreviate this as HA, as a generic Bronsted acid. And what PPA will do in the presence of a carboxylic acid is it will pass on a proton to this oxygen here to generate this compound here, which looks fairly unstable, right? Like you have an acid already, and then you add another proton to that. So this is really just going to want to lose a proton, or maybe lose water. Before we do that, I just want to refresh your memory a little bit on some Friedel-Crafts reactions that you did in second year organic chemistry. So recall if we took something like an acyl chloride, and then if we were trying to add this to a benzene ring, we would typically treat this with something like aluminum trichloride, a good Lewis acid. And so you would get some good ionic interactions between the chlorine and the aluminum, pulling electron density away from here. What was the electrophilic substituent that could now react with the benzene ring? So this was formed by the electrons on this carbonyl group coming down, and because chlorine was being pulled by the aluminum trichloride, this would leave, and you would be left with something called the acylium ion, very reactive species. So you have seen that before. Again, this is just a little chart back down memory lane with Friedel-Crafts. Acylation of phenyl groups. So apply that same thinking to polyphosphoric acid. If we protonate here in a specialized way, we now have the oxygen here with electrons. They can come down, and we've identified that water is an excellent leaving group. So water will leave, and this is now an excellent way to generate this acylium ion, analogous to what we've done here with Friedel-Crafts. Acylium ions, as you can see, are incredibly electrophilic, right? You have a positive oxygen, so this carbon here is just screaming for a nucleophile, so it can break this triple bond to a double bond and put electron density back at the oxygen. All right, so when we treat this compound here with polyphosphoric acid, you therefore know that you're going to generate some type of acylium ion. Okay, so through this mechanism that I've shown you on the right, you can now imagine that you're going to generate this reactive species. And now remember, we are under acidic conditions. Water has been released during this reaction, right? Water was a good leaving group. And we're going to deal with enols, okay? So that's the protonated form of an enolate. So you can imagine here that this carbonyl, will again pick up a proton from polyphosphoric acid. Now you have two positive charges on the molecule, pretty, fairly unstable, right? So immediately, what you're going to do is you're going to form an enol, and you're going to form an enol picking up this proton here to generate the more stable enol. Okay, and what is going to be our base? Well, it could be the conjugate base of polyphosphoric acid, or since water's come off here, water could also be used to pick up this proton to generate the more stable enolate. And because we're under reversible conditions, the more stable one will form and not the kinetic one. Let me just count my carbons. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So 1, 2, 3, 4. Okay, good shape. All right, so what do you think will happen now at this stage? You have this enol and you have this acylium ion, which is incredibly electrophilic. And enols like to react with really good electrophiles. So under this stage here, you have an okay nucleophile at this position, excellent electrophile. If these were to react intramolecularly, and recall the discussion we had lecture 22 on intramolecular reactions, first look for any potential rings. So if this carbon reacts, 1, 2, 3, 4, 5-membered ring. 5 and 6-membered rings are good. So let's take a look at what that will look like. Okay, so now your oxygen is positively charged because it has 3 bonds from that proton. And this carbon has reacted to form a 5-membered ring. So you have 2 5-membered rings that are held together through this quaternary carbon right here. And then finally, the last thing you need to do is remove this proton, which is highly acidic, to generate this product. So this is sort of an interesting way to generate unique compounds using a very gentle substance called polyphosphoric acid. And this step here, is essentially the irreversible step right here to close this 5-membered ring. Okay, I'll just make a note. It's irreversible. Well, we can think of it as being irreversible because that acylium ion that we generate is just incredibly electrophilic, and it's really not going to go back. Okay, so it's craving that nucleophile, and because it's just so electrophilic. So you can think of it as being irreversible because the acylium ion is highly electrophilic. Okay, so that's just sort of an interesting story and example of acylating enols under specific acidic conditions. All right, so finish writing that down. I'm just going to erase this board here, and we're going to go through one last example using a Lewis acid catalyzed, or Lewis acid to catalyze the reaction. So we'll call this Lewis acid catalyzed acylation of enols. The Lewis acid that we're going to use is something that is ubiquitous in organic chemistry. I don't think we've used it yet in this course, but you've seen boron before. So we're going to look at a compound called BF3. Okay, BF3. What did we remember about boron? Boron has this low energy p orbital, right? That is seeking electron density. And electrons from the carbonyl can readily add to that p orbital to form a complex. If you do that, then your boron becomes negative, and you have an intermediate that looks like this. Your oxygen here has 3 bonds, so that's positive. It's still a neutral compound. You're taking 2 neutral compounds together, they're reacting, so overall this is neutral. Now, fluorine is the most electronegative element on the periodic table. So you have seen these types of compounds before as reducing agents, where you would have something like borohydride and then the H- would attack. Under these circumstances, the F- is actually so electronegative, and you don't need a particular electrophile for that F- to become released. So you could just think of this becoming released off as F-, fluoride, and then now you have a boron in a neutral species. So just remember that boron is kind of special in this way, in that you can have this equilibrium between negative and then neutral, negative and neutral. So you can imagine once this comes off, you're going to have some population of F- re-reacting here. So this kind of goes back and forth. All right. So once we generate this compound here, what we're going to do is we're going to add an anhydride. And we've seen anhydrides a lot before in this class. Now, think back to what boron likes. Boron likes electrons, right? You could pick it up from fluoride and just go back and forth and dance a little bit. But if it sees this anhydride molecule, well, what it's going to do is you're going to now have the electrons, like we've done in the first step, react with that boron. Don't forget your positive charge here. So now you have like a bridging boron held together by 2 oxygens. Okay, so kind of a funny looking structure. So what can happen now is that you have this positively charged structure, and what we're going to do is we're going to form an enol, just like we had done over there, because we have a positively charged structure. Okay, so just some sort of weak base in solution would be able to do that. Okay, so let's make sure we have all our charges. Boron's negative, this oxygen is positive. We've now formed this, like this enolate, or this boron enolate, that's covalently bound to this anhydride. Now think about ring formation, right? We talked about 5-membered rings being good, 6-membered rings are also good. So do you see a good potential intramolecular reaction that could occur? And remember, boron is happy to go between neutral and negative. So if it releases this oxygen bond here, electrons can come down, and this is actually pretty electrophilic because it's now attached to the boron. You can imagine you can get like a intramolecular 6-membered ring formation transition state happening, bridged by that boron. So once that happens, what are we going to generate? Here's our new carbon-carbon bond. Okay, so the boron is neutral because it gave up that electron to the oxygen to form that double bond. And this is actually, again, stabilized a little bit through the oxygen adjacent now. So you have this sort of stable six-membered ring where you can get kind of fluctuations between negative and positive. So it goes back and forth, on and on. And then really at the end of the day, what you're going to do is step 2 is you're going to take water and work this up. And water, having oxygen and electrons, is just simply going to react here and break that boron oxygen bond. So what you'll end up getting I'm just checking my arrows here. This reacts here, so I'm missing a methyl group here. Make sure you put in that methyl group. So you form now this tetrahedral intermediate. This will come down, and then you'll break that off. So your final product will be this attached to that. So we started with something like cyclohexanone, and simply using acetic anhydride, or you can think of other anhydrides, you can readily form these dicarbonyl compounds that are separated or bridged between an alpha carbon. These compounds are very, very attractive. So maybe just a couple notes I'll just make here. Don't forget here we have a six-membered transition state, which is very favorable. And just some other things I guess I'll write just to be clear. So the BF3 is really interesting because it's a Lewis acid and it coordinates to both the nucleophilic enol and the acylating agent. And through that six-membered ring transition state, this type of reaction can happen. Coordinates with both nucleophilic BF3 is a Lewis acid and coordinates with both nucleophilic enol and acylating agent. All right, so I'm just going to put a couple concluding statements on this unit, on the last 3 to 4 lectures. So summary of acylation at carbon. So in general, you need to consider both the oxygen and the carbon as nucleophiles if you have an enolate. And then we could use specific enol equivalents to prevent that oxygen from reacting, so you don't get that enol ether being made. And then number 2 here, I wrote that this can be controlled by choosing the appropriate cation to complex with the oxygen, such as lithium. However, the best approach involves using specific enol equivalents like enamines and Aza Enolates. Okay, so however, if you have a chance, the best approach involves using weak nucleophiles such as enamines, or strong nucleophiles like Aza Enolates. And then finally, you can use polyphosphoric acid or BF3 to activate carboxylic acids with enols. And we just went through a couple examples. Can also use Okay, good. So we finished. I hope you liked this unit on acylation of carbon. What we're going to focus next unit is conjugate addition. So things like the Michael reaction, right? So if you have something like, you don't have to write this down, just giving you a little preview of what's up. So remember we made these enones. So now we're going to look at how we can control reaction like a nucleophile occurring here. All right, so stay tuned soon for that one. Have a great day.